Hello, everyone. This is one of a series of short interviews that I've been conducting at the Bay Area Alignment Workshop, which is run by FAR.AI. Links to what we're discussing, as usual, are in the description. A transcript is, as usual, available at axrp.net. And as usual, if you want to support the podcast, you can do so at patreon.com/axrpodcast. Well, let's continue to the interview. All right, Jesse, welcome. Thanks for being interviewed.
Thanks for interviewing me.
So for people who don't know, could you say a little bit about yourself, who you are?
So I'm the executive director of Timaeus. We're a research organization working on applications of singular learning theory. So I think we'll get into more of the details, but concretely, SLT is a theory of Bayesian statistics that answers some questions around generalization, why neural networks are able to generalize as well as they do, and therefore paves the road to applications for evals. Can you understand when your evaluation benchmark is actually going to be predictive about behavior downstream in deployment, applications for interpretability, questions like, can you detect that the model is planning to execute a treacherous turn? It's the kind of question I hope to answer someday with a better developed theory of SLT and associated tools for probing these questions.
Gotcha. So, and if people are interested in that, we had a previous episode with Dan Murfitts on, I think it's just called Singular Learning Theory, that you all can listen to.
So Daniel Murfitt, I mean, he's the one who really put forth this agenda of applying SLT to alignment, and we're working very closely together with Dan to make that reality.
Great. So before we dive into the SLT, so we're here at this alignment workshop. It's run by FAR.AI. It's the start of day 2. How are you finding it?
It's been great. So my highlight yesterday was in one of these small discussion panels. So I'm sitting here, Anka Dragan sitting here, Joshua Benjo sitting there, and Audrey has pulled up his computer with the Shoggoth meme on it, and Anka is explaining the Shoggoth to Joshua in extreme detail. Wow. I managed to capture a picture, so hopefully, we can disseminate that somewhat.
So yeah, you're executive director of Timaeus. What is Timaeus up to these days? What are you doing?
Yeah, so I mean, Timaeus does two main things. Primarily, we're a research organization.
Yep.
Right. So, in particular, the SLT for alignment agenda is sort of split into two parts.
Okay.
So there's the more fundamental side, theoretically heavy.
Yep.
And that's work that Daniel Murfitt and his students are really focusing on.
Yep.
And then Timaeus is gearing more towards applications. So taking these tools, scaling them up to frontier models as quickly as possible, trying to make progress that's meaningful to safety as quickly as possible. And so that's the work we're doing. So experiments, training lots of models, running learning coefficient sweeps. That's one of these techniques we have from SLT that we use all over the place. And research is also maybe the primary thing that I'm doing.
Okay.
So in addition to the research, we're also making sure to do outreach to make sure that people are familiar with the work we're doing.
Okay.
So that at some future date, we can hand off techniques to the labs, to policymakers, to other people who need to make decisions with what the current state of learning theory can do.
Okay. And what does that outreach look like?
That outreach looks like me giving a lot of talks.
Okay.
Some of it looks like personalized outreach, thinking about other people's research agendas, questions they might have that SLT could contribute to, and thinking about how to answer that, and then going up to those people and talking with them about it.
Sure.
And that's just something you can do.
Yeah. So one thing that comes to my mind is, I don't know whether it was just last year or the year before, but you ran this singular learning theory summer school type thing, right? I'm wondering, and which I found pretty fun, and I didn't even go to the fun bit. I just attended the lectures. I'm wondering, is there more of that in the future, or is that not quite the focus?
So that's another part of the outreach strategy, is running events. So there was the SLT for alignment workshop.
Yep.
There was a developmental interpretability workshop. It's one of these subfields of the SLT for alignment research agenda.
Yep.
Recently there was Iliad. So it was a conference not just of SLT, but also computational mechanics, agent foundations, and a bunch of more theoretical approaches in AI safety that came together.
Yep.
There will be more of that. So we're contributing to the first Australian AI safety forum that'll be running in in only 2 weeks, the start of November. So that's co-organized with a bunch of other organizations, Gradient Institute, Sydney Knowledge Hub, and other organizations affiliated with the University of Sydney. So
Okay.
these kinds of collaborations, organizing events, I think it's a key part of this.
Cool. So I want to dial into a thing you just said there, or maybe I misinterpreted it, but you said that developmental interpretability, I guess, is like a subset of the SLT for alignment. And I think to a lot of people, they're sort of synonymous, or yeah, I had the impression that they were almost synonymous. So what do you see as what's the complement, you know?
So I think the core idea of SLT
Yeah.
is something like the geometry of the loss landscape is key to understanding neural networks. So there's just a lot of information embedded in this geometry that you can try to probe, and that tells you then something about internal structure in models.
Okay.
So that's a starting point for developing interpretability tools, maybe also evaluation procedures.
Yep.
Now here are two different kinds of questions you can ask about that geometry. One is I can ask, over the course of training, how does the local geometry around my model change as I proceed?
Okay.
Are there qualitative changes in this local geometry that correlate with changes in the algorithm I'm implementing?
Okay.
That's some work that we've done so far that shows that this seems to work. That's what I would call developmental interpretability. So applying this lens of SLT to understanding the development process of neural networks. In particular, because SLT makes some pretty concrete predictions about the kinds of allowed changes you'll see over the course of development.
Right.
At least in a Bayesian setting. And a lot of the work is in implying and seeing how much does this transfer, or do these predictions from the Bayesian setting transfer over to the SGD setting.
Got it.
So SLT, developmental interpretability, take these tools from SLT, run them over the course of development. But another question you can ask is just, what is this local geometry like for a given snapshot? And maybe a question like, how does this geometry, which depends on the data you're evaluating your model on, change as you change that distribution?
Right.
If I change the distribution I'm evaluating my model on, or deploying my model on, do I see a qualitative change in the structure around my choice of weights? And we expect that correlates with something like a change in the mode of computation on that data. So it's a sign, the sort of signal you can start to use to probe out of distribution generalization. Can you understand qualitatively the ways in which different structures in the model actually generalize? And that doesn't necessarily require taking this developmental approach. I think in many cases they are synonymous, but there are questions you can ask that don't really fit the developmental frame.
Okay. So if I think about work by Timaeus that I'm familiar with, it seems like it mostly fits within the developmental interpretability side. Are there things on this, like, changing the data set and seeing how the geometry changes? Or is there work there that I could read?
Work that's coming at some point, or that we're starting on.
All right.
So one thing we've noticed is that SLT has this measure of model complexity called the local learning coefficient.
Yep.
Which you can see as an effective dimensionality, although in reality it's a richer metric than just effective dimensionality.
Okay.
So this is something you can measure, and it depends on the data set you evaluated on.
Yep.
So what we've noticed is it seems to correlate with something like memorization. So in very recent work, we looked at a learning coefficient that tells you about how much complexity is there in an intention head.
Okay.
What you find is that the learning coefficient correlates with the number of different n-grams or multigrams that a head has learned.
Okay. Where it's higher, the learning coefficient is higher if you've memorized more things.
You've memorized more things.
Okay.
There are other things like this where work by Nina Paniksari and Dmitry Weintraub looked at a grokking setting. And they looked at the size of the task that you're trying to memorize and how that changes the learning coefficient. There's a correlation there that's very, very clean. There's work on sparse parity tasks where you're looking at the number of different sparse parity tasks that your model is trying to memorize, and there's a correlation there.
Okay.
So there's starting to be, across a wide range of different things, some idea of we can measure how much a model is memorizing on a data set.
Sure. So the work by Nina and Dimitri and the sparse parity task, Are there what are the names of those papers?
That's a less wrong post.
Okay.
The work by Nina and Dimitri, and the sparse parity stuff is coming out, so that's not been published.
Okay. Do you know just so that people can look it up, so that I can look it up? What's the name of the Nina and?
Exploration of the learning coefficient for Melbourne Hackathon.
Okay.
There's hackathon
Hopefully,
in the name.
That's hopefully enough things to Google it now. Gotcha. Cool. So I now want to sort of pivot to work that, well, as of recording, you've recently put out there on the restricted learning coefficient. Do I have that name right?
Yeah, refined, restricted. We've gone through some name changes.
Okay.
We're working within
Refined. Sorry.
like the whole naming is kind of unfortunate, but it goes back and it's predates us, but we'll call it the refined LLC.
Okay. So what is the refined LLC?
So we have this measure of model complexity.
Yep.
That tells you how much structure is there in the model as a whole, and how does that depend on the data. So 2 immediate refinements you can come up with on top of this learning coefficient from the theory. One of them is you change the data set. So you don't evaluate it on a pre-training data set, but some other data set.
Yep.
The other thing you can do to refine it is to freeze some weights and measure the learning coefficient of a subset of weights. And so that's what I described with these attention heads.
Yep.
You can measure now complexity, the amount of structure in a component of the model. And so that was the starting point for this paper. We looked at these refinements and applied them to very simple 2-layer attentionally language transformers. And so what you find is, you plot this over the course of training, different kinds of heads have distinct developmental signatures. So the induction heads look like one thing. The heads memorizing n-grams and skip n-grams, which we call multigram heads, memorize one thing. Previous token heads look like one thing. There's a current token head that looks like one thing.
Yep.
And you can automatically cluster them based on these developmental signatures. And I think you can do that using a bunch of other techniques. But that's at least a starting point.
Okay.
That's one observation. What you now notice is that if you incorporate this data refinement, you can start to say something about what different heads are specialized to. So not just that different heads are different, but the ways in which they're different, what kinds of data sets they might be more important on. And so induction, when you evaluate it on a code-heavy data set, jumps up. So now the induction heads relatively experience an increase in complexity.
Okay.
And moreover, they split apart. So the induction heads previously look like they're sort of doing the same thing. You evaluate it on code, and now there's a separation where one of them seems to be more important for code.
Right.
Under additional analysis, you find that indeed, this thing seems to be specialized to syntax tokens, punctuation, that kind of thing.
Okay.
So you've got tools that are starting to probe, when are 2 different structures actually different? What is it specialized to? And this feeds into the discovery of a new kind of circuit, which we call the multigram circuit.
Okay.
These 2-layer attentionally transformers were inspired by work that Anthropic had done when they discovered this induction circuit mechanism. What we find is in these same models develop something sophisticated, another kind of circuit, so coordination between 2 layers, that seems to be necessary for things like nested parenthesis matching.
Yep.
You open a bracket, you open quotation mark, you have to close the quotation mark before you close the parentheses.
Right.
Refined learning coefficients are part of a toolkit that we're developing. It's not just tools derived from SLT, but that are showing the formation of this multigram circuit that help us discover a new circuit.
Okay.
That appears to be every bit as fundamental as the induction circuit.
Yeah. Can you tell me what actually happened? Like what tool you applied to what thing, what metric you noticed, and what's the story there and how the refined LLC played into it?
So
if it was the refined LLC.
I'm going to give a high-level story. We still don't fully understand this model.
Okay.
Right? So there's still work to be done. But what seems to happen first is heads individually memorize n-grams and skip n-grams.
Yep.
They become multigram heads. And this seems to go faster in the first layer, in the second layer. And what you notice is that the learning coefficient, particular kind of refined learning coefficient, where you're measuring how similar performance is to some baseline 1-layer model, which you treat as a reference for what n-gram behavior is like. You measure performance relative to this baseline. You notice that the resulting learning coefficient, refined learning coefficient, peaks after the second stage of development.
Okay.
At that point, this starts to decrease for the first layer, but it's still increasing for the second layer.
Okay.
So heuristically, the model seems to be losing information about multigram prediction in the first layer.
Okay.
You can verify this in a handful of cases where you actually notice that there's a migration, for example, of a multigram from layer 1 to layer 2.
Yep.
But you also notice that now suddenly the tokens that different heads seem to be involved in are changing, and now there's coordination. So one of the layer 1 heads seems to be very involved in the same kinds of tokens that a different layer 2 head is doing.
Okay.
You can actually verify by certain kinds of ablations and path ablations where you only ablate the outputs of these heads into the input of this head in the second layer, that it needs coordination. So the model's actually passing information forward now to second layer heads in order to predict nested pattern matching, or that wasn't the case before. What we're noticing is, so we're still using ablations to verify that there's coordination going on here. We're looking at certain kinds of composition scores to verify that layer 1 is feeding into layer 2. They're reading and writing from the same subspace. There's other analyses where we're looking at, if you ablate this head, which tokens are maximally affected across the data set, and actually looking at a bunch of those examples. So all of that analysis is going into identifying a multigram circuit. But this observation that information might be migrating from layer 1 to layer 2 is something that can set you off. And I think that's something that we'll observe more generally as we scale up to larger models, these kinds of signals.
Gotcha. And yeah, so if people are interested in reading that paper, what was the name of that paper again?
Differentiation and specialization in attention heads with the refined local learning coefficient.
Great. Well, thanks very much for coming here and chatting with me.
Thank you, Daniel. We'll see you soon.
See you around. This episode was edited by Kate Brunotz, and Amber Dornace helped with transcription. The opening and closing themes are by Jack Garrett. Financial support for this episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafeyev. To read a transcript of the episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.